Welcome to the C O Corporation's series of videos about software engineering. The topic of this video is C++ objects. Before proceeding, make sure that you have already watched these other videos first. We will be discussing these topics. To watch these videos, look for the links that are listed in this video's description. A C++ class defines a custom type. When used to define an object variable, that class is instantiated. Enough memory is reserved to hold values for all three data member integers. The same class can be instantiated multiple times. These two object variables have their own separate values for their data members. Imagine the computer's memory as being the land of the earth. Each object is given its own separate territory, carved out within that land. A member function is usually written with the intent of manipulating one specific object instance's data members. When you call the add function on the object called OObject, it doesn't affect the data members of any other instances like OAnother. Notice the syntax for defining a member function. In its implementation, we use its fully qualified name, consisting of the class name, then a double colon, then the function name. Just like any ordinary function would, this member function has a return type, parameters inside parentheses, and a body of statements inside braces. The member function also must be listed within the class definition, but this time a single semicolon is written in place of the function's body, and the name is unqualified, meaning only the function's name is written. There's also another way that you could write a member function. The implementation could be skipped altogether, and instead, its body could be written, instead of the semicolon, within the class definition. Some beginning programmers have incorrectly thought that this inline form is guaranteed to be faster because of the compiled code treating it like a macro that skips the overhead time required for function calls. In truth, there is no such guarantee. Whether or not the compiler makes an optimization of that form is entirely up to the compiler's own judgment. As an application programmer, you should not worry about that difference. Either write your code within a separate implementation or within the class definition, whichever is more convenient for you. Often, the implementations of all your member functions are collectively written together in a C++ source file dedicated for that class. And the class definition is moved to a separate header file. The preprocessor's include directive is used in place of where the class definition would have been written. Your custom type can be used by other code, such as this doComputation function. This client code is often modularized into its own source file. The source file containing this doComputation can be separate from the source code that had contained our implementation of the add function. However, this source file does still need to contain the same class definition code. Again, this is usually conveniently accomplished by a preprocessor include. Sometimes your client code doesn't need to access an object's data members nor call any of its member functions. Sometimes all your client code needs to do is to possess a pointer to the object. In that case, you don't even need to include the class definition. In this situation, you only need to inform the compiler that CR calculator will be the name of some custom type defined somewhere else. This is done with a forward declaration. By the way, A similar type of forward declaration can also be used for ordinary functions in situations where you want to move their definition into a separate source file. Memory is created for a variable when it is defined, and that memory is destroyed when that variable goes out of scope. That's also true for an object variable, except that in this case, the amount of memory is a little bit more, enough room for 3 integers. For object variables, something extra also happens at the beginning and ending of its lifetime. At the beginning, after memory has been created for the object variable, C++ automatically calls a special function, the object's constructor function. This constructor is a good place to initialize the object's data members. Notice that a constructor is always defined using the same name as the class, and it never specifies any return type, not even void. The most common purpose of a constructor is for initializing data members. However, notice that these statements are technically not initializations. Technically, they are variable reassignments, because the data member already has a value before these statements were encountered. Consequently, C++ invented a syntax to describe how we want the data members to get initialized as soon as their memory has been created. A function can be overloaded by providing more than one implementation for it, each implementation having a different signature of parameters. When the function is called, the compiler will choose one of the implementations based on what parameter values are given in the function call. This same overloading can also be done with a class constructor. Here, we've written 2 implementations for the calculator constructor. One implementation expects no parameters, and one implementation expects 2 int parameters. Currently, we are calling the no parameter version. To instead call the 2 parameter version, we change the object variable's definition so that it looks this way. Don't be confused by these parentheses. This line of code is a variable definition, not a function call. Although every object variable's definition does result in some constructor being done. If you don't write any overloaded versions of a constructor, then the compiler will automatically provide a default constructor, which expects there will be no parameters. For a variable like this ivar, its memory is created from within a portion of the computer architecture called the stack, and this memory gets discarded when the variable goes out of scope. In this case, that happens when the doFirst function is finished. Instead, you could dynamically create memory from a pool of memory that won't go away at the end of the scope of doFirst. This is now a pointer to an int. DoSecond can dereference that pointer to manipulate the integer, possibly even reassigning it. Be careful, this memory will leak, wasting resources that will never get reused for anything else unless you manually indicate when you are done with it. You can indicate that at any appropriate time by calling free. These malloc and free come from the history of C programming. When using C++, we usually instead use new and delete to accomplish the same thing. When using C++'s new form, we can additionally specify an initial value for the integer. Dynamic memory allocation can also be done with objects. If we didn't use dynamic memory allocation, then OVAR would get discarded as soon as it goes out of scope at the end of do first. But with dynamic memory, the object continues to live on. In do second, we can still access that long-living object by dereferencing a pointer to it. Dynamic allocation can use a constructor that expects parameters. The syntax looks like this. Because of operator precedence rules, these parentheses are not needed. In fact, we could combine the dereference star operator with the member access dot operator. When combined, they form an arrow operator, which accomplishes the exact same thing as the prior code. Inside of each member function, the compiler has already automatically defined a special pointer called the this pointer. The this pointer points to whatever object instance is being manipulated by that member function. When a member function refers to a data member, that is actually a shortcut. What is actually happening is a dereferencing of its this pointer. You could actually write your code this way if you wanted to, but we usually don't. When we are writing various implementations for an overloaded constructor, a particularly useful one is the copy constructor. The copy constructor is implemented to initialize this new object by copying information obtained from some other already existing object. Either of these two syntax forms will cause the copy constructor to be used. This copy constructor is also used when an object is being passed as a parameter into some function, assuming, of course, that the function signature hasn't added any indirection, such as a pointer to that object type. If you don't write a copy constructor for your class, the compiler will provide one for you automatically.